Alright, thanks for watching, and today I would like to derive that mysterious formula that we have for line integrals of a function. So let me just quickly remind you of the setup. So the setup is, again, we have some surface, f of x comma y, and some curve c. And again, this is c is in the xy plane, and f is in the xyz plane. xyz. And what we'd like to do is find, again, the area under the fence of the fence under f and over c. Some may say it's very fancy, right? Okay. All right, and again, the idea is we want to find this. The question is, how do we do this? So the idea is with this parameterization. So suppose, again, we look at this curve C, and here's maybe a better view of this. So this is our curve C. And again, suppose you parameterize this. So this is x of t, y of t, with t goes from A to B, for instance. And now let's suppose the following. Suppose you start at the point, should be here, but just for clarity, suppose we start here and we change x and y just a little bit. Just so that they have this little change in x, dx, and this little change in y, dy. Then notice the following. This diagonal, well, it's pretty close to the curve. In particular, you may notice it's almost indistinguishable from the curve. So here I exaggerated this, but in general it should be something like that, right? That you can't even see. Now, so we have this thing ds. And ds is this change in diagonal. Then, what is ds? Well, notice we do have a Pythagorean theorem situation going on. dx dy and ds. Then notice by the Pythagorean theorem, ds is nothing else than square root of dx squared plus dy squared. And in fact, that's how you should remember this, especially when you do the formula for line integrals. Now, here comes a little trick. So the trick is, as usual, use the chain rule. So the chain rule. Because now, again, super important trick, that's why if you're my student, you should watch this video, it's very important. Namely, dx is nothing else than dx over dt times dt, which becomes, because we parameterize this, x prime of t dt. And similarly, dy equals dy over dt times dt, which is y prime of t dt. And so using this, all we need to do is just plug in the formula for ds. So then what this becomes, ds is again square root of dx squared plus dy squared. And that becomes square root of, again, x prime of t dt squared plus y prime of t dt squared, which is square root of x prime of t squared dt squared plus y prime of t squared dt squared. And notice there's this common factor of dt squared. So we pull it out, and if you do square root of that, it becomes precisely what we want. ds is square root of x prime of t squared plus y prime of t squared. And now, what is the line integral? It's precisely integral of f. The line integral is integral over c of f ds And then you just basically plug in that formula. So f is just, f at your point x of t, y of t. That integral, again, remember that picture? We had c goes from a to b in this case. And we have, this is x of t, y of t. Right? And then c goes from t equals a to t equals b. This, again, that just means you plug in x of t and y of t. And ds is just this thing here. So square root of x prime of t squared plus y prime of t squared dt. And that's how you get the formula. And again, if you want geometrically, what is happening is, again, you want the area of the fence, right, over C and under F. Right? Kind of what is happening here, while the height is still F, but at that point. Right? So this height is F of x comma y. And the width in this case is not dx, but this little ds, right? This little change in the diagonal, and what is happening is it gives you this little rectangle which is close to the area, and then you're just summing up those little rectangles, which is why you actually get an integral which represents the area under that curve. Well, yeah, area under that fence in some sense. Alright, I hope you like this, and if you like this and you want to see more math, please make sure to subscribe to my channel. Thank you very much.